So I just, from the previous presentation, I just jotted down fair payments and quality of service. I thought I'd point out that if I don't happen to cover this during the presentation, it would be a good question to ask at the end. So, hello, my name is Ben Smith. I work at Gnosis. I've been, oh, whoa, no. How do you stay? Okay. I've been we've been doing a lot of research in decentralized exchange mechanisms, and more recently, a lot of implementation. So I'm quite heavily involved in both the research that's going on and design decisions, implement, and right down in the implementation details. And what we've been doing a lot for the last little while is trying to build a scalable, fair, and truly decentralized exchange mechanism on the Ethereum blockchain. We've got a brief overview here. I think I'm going to spend the first third talking about the decentralized exchange mechanism itself. This is actually describing an exchange mechanism as an optimization problem, and then talking about how we have a gamified order matching. Those of you who are familiar with all the different abbreviations, proof of work, proof of stake, some people like to call this proof of optimization. I'll leave it to you to come up with the abbreviation. What we'll get to in the second third there is using Ethereum as a transaction register. This is essentially about how we can achieve scalability with a network that is sort of clogged. And once a user base gets there, we need to be able to scale the number of orders, the number of accounts, and the number of tokens that can be exchanged. So we'll talk about having minimal on-chain storage that's still as secure as the Ethereum network, ensuring data availability, and finalization, specifically snark proofs versus optimistic rollup. How many people in the room are familiar with rollup? Not so many. Good thing that I have a slide that describes the gist of it. Lastly, I'll talk about our specific product. It's loosely being called the dƒusion exchange, subject to change. However, we've got a proof of concept that was meant to be released on the testnet last week, but there's a few little minor technical difficulties, and we hope to have something for our proof of concept on the mainnet. This will be the sort of unscaled version. I'll give a little table sometime at the end as well, comparing sort of the pros and cons and balance and scoring of an entirely on-chain protocol, something that uses snark proofs, which is ideally the holy grail in this field, and then optimistic rollup, which is somewhere in between. So the first thing we're going to talk about today is a decentralized exchange mechanism, and I'm just going to throw a mouthful at us. We're going to be talking about multi-token batch auctions with uniform clearing prices. So to break that down into just three components, multi-token. This means that orders can be placed between any asset or listed pair. I'm not going to, the motivations for building an exchange in this way, I'll point out as they go. Once we've described the whole protocol, I'll point out a few nice features that come with doing things in such a way. Batch auctions, this is contrary to traditional exchanges. In a batch auction, orders are collected over a finite period of time and placed together, aggregated together in a single order book, which is also contrary to traditional exchanges in the sense that usually you see orders placed you see an order book between two token pairs. Here, we aggregate all of the orders into one batch and try to do the order matching this way. Uniform clearing prices is simply that prices are determined for each asset, and the exchanged or any touched orders are all settled at the prices that were determined. I guess no slippage, if this is a term that people like to use. So here's another mouthful. I've also taken all the animations out of the slide because they distract me. So some of the slides are a little bit bigger than others. Batch auctions as an optimization problem. The first point here is simply orders collected between any listed token pair over a predefined batch time. The really exciting part on this page is modeling the exchange as an optimization problem. So this optimization problem, which should fulfill the order matching and prices, is to say maximize, actually trader's utility is not a typo there, but the objective function is subject to ongoing research, as we will talk about. This is another good question to ask if you're looking for questions later. This trader's utility could be replaced with anything or other things such as trading volume or trader's surplus or trader's welfare. Some of those terms are equivalent, and in fact there is a relationship involving summations amongst all of those possible objective functions. So in an optimization problem, we always try to optimize some real valued function and subject to some constraints. And those constraints here are that limit orders are respected. Price coherence, in the sense that the price of A for B is the multiplicative inverse of the price of B for A. Arbitrage freeness is the fact that you don't wind up with more or less if you make an exchange along a cycle. Us mathematicians might like just the term transitivity or something. Anyhow, and preserved value, which says that I like to call it conservation of value for the physicists out there. That's that nothing is created or destroyed in the exchange, or that the sum of all the value of one token being sold is equal to the sum of all the value of the token being bought. So what happens here is that we try to perform order matching with an aggregated order book according to these constraints, which sort of implies that the fairness of this exchange is inherently baked into the protocol itself. So providing a feasible solution of any sort implies all of these aspects by default. So, so one thing that we get out of this that we don't see in traditional exchanges, by aggregating all the orders between all of the token pairs together, is that we get the possibility for ring trades, which I believe there would be a lemma for this that immediately implies, if our objective function were trading volume, that this would imply more trading volume than a traditional order book of A for B, since you could have someone who wants to buy, A for B, someone who wants to buy B for C, and someone who wants to buy C for A. And in a traditional exchange, nothing would happen because these orders are sitting in different order books, whereas here we get something called ring trades. I like to use this example. People buy toothpaste for money, people buy money for Bitcoin, or Bitcoin for money, but what happens if I want to buy toothpaste for Bitcoin? I don't know. So you might be able to find an order that matches in this situation. So this is just a nice little picture here about how we've aggregated the order books, and this is based on real data that we get our information from. We do a lot of our simulations with Kraken data, so the exchanges, the orders that are placed on Kraken. So what we find here is these are actually a bunch of feasible solutions, and the color gradient is the trader utility. I'm not sure, actually, when this graph was made, I think we were experimenting with trading volume. But just keep in mind that those things are different, and there are things to consider when using different objective functions, such as volume and utility. And what we find is we can get a good trader utility. It's just a cute little aggregated order book. So these are traditional order books between two token pairs, and they're all sort of put together. So this is just the how the auction process would run on the Ethereum blockchain. This isn't quite the implementation details, which we'll get into in a little bit. Hopefully there's a clock somewhere. Okay. So we have our order collection. These little arrows here sort of suggest that there might be a form of offline order collection. But there's also, users can choose to sort of submit their orders directly to the blockchain itself and ensure that everything is available for them and everything is fair. Later on, when I talk about the fact that we have a grant program, implementing sort of integrating off-chain order collection in a secure way with data availability is something that our company might offer grants for. There are other people interested in that as well. So order collection in the first phase over a finite period of time, as we mentioned before. And this is, I guess, where I point out the fact that we have a sort of gamified order matching system here, where anyone can be a solver. So at the end of a closed batch, anyone can take all the orders that are there, and all they have to do is find a feasible solution to that optimization problem with the highest objective value. So it's almost like a bidding, like an auction for being for doing the order matching. This is also how we sort of achieve decentralization. There's no centralized operator matching these things. Anyone can be a solver. And of course, there's a sort of stake reward mechanism involved in being a solver. So what happens during price calculation is there's a little window. Of course, what we get by doing these batch auctions is slightly slower settlement. Slightly slower. We're actually working with 5 minutes, 5 minutes, 5 minutes, more or less, with overlapping order collection. So in the second phase, people sort of bid. They don't reveal their solution yet. They bid. They say, I have a feasible solution with objective value this much. I have a feasible solution with objective value this much, et cetera, et cetera. And the blockchain itself can say, okay, sort of record without revelation. So there's sort of a bidding followed price or order matching, price finding, order matching phase, followed by solution revelation phase, where whoever's currently got the winning solution can submit it to the chain and perform what's the final stage here is the trade settlement. They provide all the order matching, and then in a single transaction, everybody's account balances are updated with the executed orders that they placed between any tokens. So just to summarize this section here on the decentralized exchange mechanism, we achieve decentralization in the sense that anyone can be a solver. This is economically incentivized. The solving and bidding period, approximately 5 minutes. Solvers submit bonded claims attesting to the fact that they have a feasible solution with objective value of X. And then there's a little short revelation period where the smart contract selects the winning bid, and winning solution is provided to the smart contract. And once finalization of the state transition or the auction has been achieved, the solver is then rewarded. And keep in mind the question about the things that you mentioned. Right, so I don't know if this is going to be too technical or not. I don't think so. I tried to include a lot of pictures. Just about sort of achieving scalability is one big thing with the Ethereum network. We can't just have a whole bunch of people submitting big orders to the blockchain and processing thousands of them at a time. So achieving scalability using Ethereum as a transaction register. This is what I mentioned before or referred to before as roll-up. Luckily, I've got some slides here describing it anyways, but a lot of our work is sort of inspired by this roll-up nature of things. So the smart contract itself does not actually know each user on the platform's account balance. All that is there is a sort of hashed representation of the account state tree. The account state tree holds all the users and all the different tokens that are listed on the exchange, all in one smart contract. But the contract itself only knows the state root. So all this other information is archived off-chain. This is sort of how we achieve scalability. And whenever an auction is settled, essentially the account state tree is updated and the root is updated. So what has to be done what's done to process that for the most part is that you provide a snark proof that this was computed correctly along with all the information that went into it. Actually, you don't provide the information that went into it ideally because the information was passed through earlier as payload information. So all the orders that were placed on this contract are sort of passed through and emitted, say, as an event. I'll summarize this in a slide a little bit later. But for the most part, account balances are represented by root hashes. transactions are collected on-chain as payload and hashed. So the contract doesn't even remember the information that was passed through, but it is there in the transaction receipt, more or less. Anyone can process these transactions by performing one of these state transitions, along with a snark proof that this state transition satisfies what it should, the constraints of the protocol. And this security is enforced by snark, and we get about 25% or 25x scaling in this case. This scaling is subject to improve with, I believe, they're reducing the amount, the gas cost of payload information significantly on the Ethereum network at some point, although this protocol would work with or without any upgrades to the Ethereum network itself. So there's a few different transition types, more or less. People would enter into this protocol, deposit, withdraw. These deposits and withdrawals can be implemented without the application-specific layer of the exchange. Of course, though, nobody wants to deposit and withdraw onto a platform that doesn't have a real application. But in fact, everything is sort of processed in batches in the same way. Deposits, withdrawals, and auction settlements all are the three different types of state transitions that exist on this platform. The requests that are made to this platform are made to the smart contract as payload information, but not really remembered. This call data is emitted as an event and sort of, in a sense, broadcast as logs. The Ethereum logs are broadcasting all the requests that are being made to this platform. So this is where you achieve your data availability. And processing is done all off-chain. This is actually quite nice because you reduce the gas costs and all of the computation that needs to be done by a distributed system. By processing these requests, so you batch together all the deposits, you batch together the withdrawals, and then at some point you say, okay, this withdrawal batch is closed, it's time to process all of these, or this deposit batch is closed, it's time to process all of these, and that says, okay, I'll go update all the account balances according to the requests that have been made, and update the state root of accounts. And all of this can be done off-chain by a single machine that provides either a snark verification of their computation, or we work with an optimistic version, which is a sort of challenge response. Thank you. Uh-oh. Boop. Boop. All right. So just some points. Section 3 here. This is sort of some of the infrastructure. Smart contract, event listener, archive node, smart contract driver, keeping track of all the information that's been emitted by the smart contract itself. And this is sort of interacting with the solver and updating the state of accounts on the contract. So this is just the basic infrastructure diagram for this thing. And I just want to talk about where we are and what we have at the moment. This proof of concept is an entirely on-chain version of the exchange mechanism that I described in the first third. It's between stable tokens, and I'm not a financial advisor, so I'm not going to get into the attractability of such a thing, but it's a bunch of listed stable tokens, and there are some other people on my team who like to, who have some information regarding liquidity providers and users and how they all interact there. Same exchange mechanism, entirely on-chain, building it right before building the right it. You get ring trades for better liquidity. Liquidity is bundled over time as the batching. And it has a Uniswap-like onboarding process. It's as easy to use as Uniswap. I think this is really important. These are some really key features for what we achieve in terms of optimization or whatnot. Gas cost for the on-chain version is horrible. EVM storage for on-chain is horrible. The pure rollup is the holy grail. The only thing that we don't really have right now is the computational feasibility to do this in a reasonable amount of time. Once we have that, this is definitely the best avenue. I've done a lot of work in the optimistic rollup sector. So we actually started building this product backwards. And now we're in a place where we're ready for these and we know the feasibility. But we're going to try to get something out there for people to see if they really want it. Optimistic rollup has high gas costs in the event of a challenge. The orange represents a gray zone where in some situations it costs a lot of gas. So a few open questions and construction sites. Snark capacity for scaling orders, accounts, and tokens. Competing solvers is something that we'd be probably interested in giving out grants for. Economic efficiency in terms of what the objective function, making sure ensuring market orders are executed fairly. This protocol is really good for limit orders, but market orders, we need to continue doing good research on the objective function. Order collection, right. Anyways, we have a grant program. We offer funding. There's a lot of construction sites in this area. Super happy to talk about all of it. I'm not going to include a bunch of links, but we also are entirely open source. We have a lot of research. This is a paper that was recently accepted at a different conference. Yeah, you find a lot of our stuff at Gnosis GitHub. Thank you. I assume there's no time for a question, right?
Yeah, why don't you do a question?
We do have one.
Hi. Great talk. I was wondering, let's say you have multiple ways to solve the optimization problem. It seems there are, right? And I've put in money for this trade, and I want to go solve it in a way that's favorable to me, and then post a favorable solution. How do you handle some kind of problem like that?
So there's two things there, actually. So trying to make it favorable for yourself will likely yield a lower value in objective function. So this is certainly one way. If you're constantly making it favorable for yourself, you would unlikely be selected by the contract as the winner. And another thing is also, in the open research area, there is distributed key generation for having sealed bids. This is research that we don't have time for doing right now, but actually the protocol describes sealed bid batch auctions, where they're not actually revealed until the batch is closed. And so you don't have access, you can't really front run by knowing information about the orders beforehand. I hope that helps.
Yeah, that was great. Thanks.